Welcome to the class. All right, so we are now to block parity, and we can see that the parity for each row is this last number. The parity for the columns is at the bottom. Therefore, if we switch a particular bit to be an error, then the parity for the row and the parity for the column will allow us to identify which bit was changed.
Now, what if
yes.
you have two in the same row?
All right, so let's try it. So now we're going to set this one to a 0 and this one to a 1.
Mm-hmm.
And as we are looking at it, the row parity is okay. That's fine. But as we look down here, this particular parity bit is not happy, and this parity bit is not happy. Okay? So we now know that somewhere in these two columns there are problems. We no longer can fix them, all right, but we can at least detect them. So these systems for detection of errors are not perfect, and they have ranges of accuracy. Okay, so this particular block parity allows us to fix single bit errors. Okay, another way to deal with these kinds of problems would be to send the same data multiple times. Right? Why not? So if I want to protect the first row and make sure that it arrives at the other end, I can send it twice, and so then the receiving device can compare and see perhaps where the problem is. Well, that wouldn't work as well yet, because see what happens if I switch this bit. The receiving device will not know which one is correct. So hey, why not send 3 copies? All right, are you getting it? Right? So 3 copies, and so now if I modify one of them, I can check with the other 2 and see which one is it. Now, what would be the sort of issue with doing it this way? Yeah, you're sending 3 times. So now you're downloading, for whatever reason, an 8 gig movie, right? And you have to download 3 times as much. So these types of systems are not used in telecommunications because of the overhead that they would create. Now, is it cool? Yes, and it probably would work efficiently, but it creates a lot of overhead. Historically, though, we have error correction systems in place that use it. Now, I'll give you an example. So, long time ago, when books were written, and you can think about even the Bible, they would write the first copy, and then what would they do with that? Yeah, they would copy it multiple times. Okay, and if you look into history, some of the people that did that, monks and so forth, they would count all the letters on the page, include the number, so that quickly they could verify error detection system. But now, as you copy the same page multiple times, you see when errors take place, you can compare the other ones. See, and then you would know perhaps you can identify based on majority vote which one has the error. And I think some years ago when we had these the Dead Sea Scrolls in Grand Rapids, that subject was sort of discussed a little bit more because those Dead Sea Scrolls were like 1,000 years discovered after 1,000 years difference from the other ones available, and they were comparing, and they were pretty close the same. So those multiple copies do work historically. Yeah, so these error detection systems have been in place for a long time. So let's talk about what are some of the error detection and correction systems available today that actually are a little bit more efficient. And parity, block parity is great. It helps us to, reuse the data that we already are sending, within a block. All right, to make us more accurate. So The next thing that I'd like to mention is Hamming code. Okay, Richard Hamming is or was a scientist with a degree actually from University of Illinois, so just across the pond. And in 50s and 60s, he worked on development of methods to make sure that when bits are sent across the wire, there's a way to make sure that they are accurate, and if possible to recover the data on the other end. So we're looking quite a few years ago when these things been developed. And so we have this expression of Hamming distance or Hamming code, all of that because of his contribution. So here's how the Hamming code would work. We will start with Hamming code 7,4, meaning that we are sending 4 bits of data, and we'll create a 3-bit code to verify it. So let's start with 0110 as the data. So this is our data. Now 0110 in 0110 in decimal numbers, what would that be? So this is binary, and other than looking like a beginning of a bicycle, right? What would it be in decimal system?
Oh, in decimal, it would be.
This is 0, 0 plus 2 plus 4. 6. Very good. So if we are looking at the value of this, it's 6, and so we care that this 6 arrives safely on the other end, right? That's why we were doing this. So we are going to create additional 3 bits, and actually in the syntax of Hamming code, the first 2 bits of the code come first, then our first code of data, then the next bit, and then the rest of the message. All right, but that's just how that's defined in the spec. So our mission is to determine what these 3 bits are going to be. So let's figure that out. We're going to use a Venn diagram, and I'm going to mark these circles as A, B, and C. Now we're going to plug in our data into those circles. Okay, plug in data into those circles. So we're going to plug it in as 0, 1, 1, and 0. Okay. Now we just have to create the parity bits. Okay, even parity bits. We have to put some data inside of the empty spaces. Let's start with the circle A. Circle A, in its scope, has 0, 1, 0. To make it even parity, what do I have to plug in?
1.
All right. All right. Now, in the B circle, what do I plug in as the parity? All right, it's a 0 because it already has 2 1s. So it's a 0. And then in C, 0. All right. Now, the way this Hamming code 7.4 works is if I lose any of the bits, okay, by losing, it's just not gone, but basically it errored out and now it's a 1. Notice what happens. The A circle with its parity bit says there's something wrong, because 0, 1, 1, I should see a 0 for parity. So A circle is unhappy. It's like the little baby crying. We don't know what's going on, but that's unhappy. Then B, it's a 0 with 3 1s, also unhappy. But if we look at a C, this is all correct because it only has two ones. So now we know that the bit that is only common to circle B and A is at fault. And now we put it back to be, what did we do here? 0? Okay. All right. So this looks very much like triangulation, like in a GPS signal, right? And that's what we're doing. We're using these additional parity bits to triangulate the rest of the system. And there are other Hamming code improvements. The 8-4 code, for example, simply puts another circle on top of the whole thing and adds another parity bit that verifies the whole thing. So now I have 3 ones. I need to add another one, okay? Because if 2 elements get switched, it's more difficult to find that out. So this parity bit helps us to increase the level. So now that I figured out I have a 1 0 0, I just plug in 1 0 0 in the actual transmission, and now I'm sending these numbers. You see, the position of them is important too, because as the number goes through, we are transmitting data that's inside of the other parity bits. So it isn't like the parity bits come first and then the data later. And we send this out. And this is sort of a self-protecting mechanism, but it also allows us recovery of some data at some point. So that's Hamming code. And for... Yes, please.
4 bits, the max that you can send me or what do you do for 8 bits?
Right. So you can use additional arrangements for other codes. This right here is just a quick view of that. Let me just see if they specify here. General algorithm. So this one has 1, 2, 3, 4, 5 parity and 15 data bits. Okay, so you can extend it forward, and here, you know, different Hamming codes. But the idea is that to draw it on the board, this many circles starts to be a little bit confusing, but you can extend it forward. And then this is the diagram that would show the data goes inside, and then the parity goes on the outside, and we can go ahead and then forward it. And here's an example of the parity being over the entire piece. I believe in this article you can, if you're interested in doing so, you can actually get more examples right here, where you have, hey, here is a data set. Well, that's not a good example. Let's try this one, or let's try this one. So you plug in 1 0 0 or 1 1 0 0. Okay, then you calculate the parity, and then you add these are the parity bits right here, the red ones. Okay, and so it's really neat how that works. And if you consider that this has been working in telecommunications for a long time, when you use programming or any other elements of computer science, you can use some of those solutions. It sort of stretches our mind in what's been invented to protect those bits. Does that make pretty good sense at this point? Okay, so more examples on this page that help us to see the data inside, right? The data inside, and then the parity bits that have certain range, and the resulting protection of the data. Yeah, so the Hamming code, great read as far as what he did and some of the other projects that he was working on. So let's move to some other error detection techniques. Checksum is another one. Okay, here's how checksum would work. Let's say that I am sending the word grcc across, okay, and I would like to include a verification information. In ASCII, what does grcc stand for? Grand Rapids Community College, yes, that's what it stands for. But if we look at the ASCII code itself and look at the table, then capital G, right? I'll just look at the red pieces here to find my place. Capital G is right here, and the decimal representation is 71. So we'll write down the GRCC, that's 71 plus R right here, 82. 71 plus 82 plus, let's see, GRC 67. And the last one, very good. All right, not everybody's sleeping. Oh, good, good. So 71, 82, 67, 67. And that is equal to, all right, 377 at the end. 287, all right? So when you send GRCC, you send 287 along with it, and the other party, they don't know if you were sending GVSU across, they don't know that. But they can verify that, GRCC will sum at 287. So that's a checksum method. This checksum method is used today more for verifying downloads than in actual data transmission, because there's a lot of overhead in calculating these values. There are some more efficient ways at the computer level, ways of calculating, and we'll talk about CRCs, and that's really the only advantage is when you can calculate something more efficiently, then that becomes sort of the most widely used system. So what I want to talk about is how downloads are often verified. So let us go to a website that allows us to download software. We'll go to Projects, Alphabetical, and let's go to the download section. And notice that along with a program, I can verify my download, okay? And these are all checksums that are calculated in some other way, not perhaps ASCII sum, but they are calculated so as to represent the program itself, whatever the binary file. So the binary file does not have to be a text file. It can be an image. It can be a compressed file like this one right here. So let us see how we can verify this kind of a file. Let me start a program here that allows me to log into a remote system. And let's go here. Perfect. So now the first thing that we want to do is we want to download this file. We're downloading the software, and as the download takes place, errors can occur, right? So we don't know at the end of the day if this file that I downloaded is accurately downloaded. Other things could happen. There could be hackers, man-in-the-middle attack, where they are modifying this as we're downloading it, or maybe someone hacked their website, and now I'm downloading a file that I really don't want to execute, right? So these verification mechanisms here allow me to run on my own system an MD5 checksum, and then all I have to do is compare the checksum that they have with mine, right, to see that, hey, this is the file that is that has a consistency to it. most of the time you'd like to see maybe the checksum being downloaded from one place and the file from another, because if someone hacked into this site, they could have, republished the checksum. But you can send the checksum through an email, and then you can download the file, and then you can use it to verify. The other checksum that's used here is the SHA-1, and we'll talk about these mechanisms when we talk about security and encryption. But this one I can also execute, and again it should match whatever is published. So we are talking about a checksum as a mechanism to validate transmission, validate the result of the transmission. Excellent. So we talked about Hamming code. We talked about parity. We talked about checksum. Let's talk about the CRC, or the cyclic redundancy code. Okay, this is a very widely used method, even on the hard drive. As you save a file, the CRC code is saved with your files. And the reason why that's so is because the calculation of the CRC, while difficult for human beings, is very easy for the computer. Okay, it just uses an XOR operation and very quickly moves the bits around to do that. But the way it happens is the computer is going to take a string of zeros and ones, okay, and it's going to put together multiple frames to create a long binary number. It takes it then as a number, then divides that, okay, by a specific predetermined number, and then it looks for the remainder of that calculation. Because it does that, you see, it no longer has to track a very long number. Now it just tracks that code, the remainder of the transaction, so that later on, when the same sequence of zeros and ones is divided on the other end, the remainder has to be the same. Okay, it's not that simple, because actually what happens is they end up including the remainder in the transmission, so that the resulting calculation is always 0. Okay, the general idea though is that we take a long string of zeros and ones, and by dividing and using the modulus 2 function, we end up with a remainder. So here's what modulus 2 would be. If you are dividing, let's see, 7 divided by 4, okay, it's 4, and then remainder is 3. Okay, if you divide 11 by 5, then the remainder is 1. So you can see how, even though the numbers are larger, the remainder is always fairly small. All right, and if I send 11 over the wire and they divide it by 5, they're going to have the same result. So now if you can have a really large number, you come up with a remainder. It makes it very, very efficient. And so those CRC, those cyclic redundancy codes, and there is a whole number of them depending on what polynomial expression you're using. And what's been found is that some expressions are more efficient than others. Okay, so today we have not only the theory but years of practice to show that that this works well. But even with this in place, let me take you to a slide here. Even with this in place, the CRC is not perfect. Okay, it has 100% in single bit errors, double bit errors. Okay, but there are some oddball situations that even the CRC can miss some small error. All right, chances of that are very, very small, of course. So as you read files from the disk and you see a CRC error, it means that the file is corrupt. There was some change that took place, and now this bunch of zeros and ones that was read in is just not right. That's also used in CD music. So as your CD-ROM scratches, see, some of these errors can be identified, and they actually have a process where you can recover some of this data. But then the more you scratch, it just goes beyond the data recovery capacity. So CRC is sort of the #1 way of detecting errors. It is not very helpful with identifying the problems because it works on such a huge data set. Okay, it's not going to tell you which bit is broken, but it's going to at least validate the data, which is what we really care about most of the time. Unless you have some kind of a mission to Mars project, okay, and then what happens, the data takes a long time to arrive at the spacecraft, right? So you can't simply say, the CRC is wrong, please resend, because it takes forever to do that. So in those situations, you may be better served by including some redundancy or Hamming code or parity type situations so that you can actually fix the data on the other end and you don't have to just say resend. On the same subject, well, not of the Mars, but of the recovering data, data detection takes place not only in the data link layer that we are discussing, right? As this data flows, we don't know if this is a picture of someone or if it's an email, text, we don't know what it is. It's just zeros and ones for us. And we try to be careful and detect whenever errors take place. Well, later on, when these zeros and ones are put together into IP, so the network layer, the header for IP also is going to be validated. And if something is wrong, it's going to be acted upon. And here is why. If packets at the IP level come in the wrong order, so let's say I got packet number 5 because there's a sequence to them. I have packet number 5, and now I got packet number 10. I'm missing 4 that are in the middle. I can't allow, that's an error. From the data perspective, everything was perfect because all the zeros and ones for both packets are fine. So we have to have error detection at higher levels to validate that this actually makes sense. So at the IP level or at the TCP IP, at the transport layer, we also are going to have a validation process. And at those layers, you see, what we can do is we can say, go ahead and resend the packet that you tried to send, or if the packet comes out of order, I have 5, now I have 10, I can keep the packet number 10, I can specifically request packet number 6, number 7, number 8, number 9, and when those arrive, I can take out of the buffer the packet number 10 and then request 11 and move forward. All right? So different error detection processes for different levels of the OSI model, and they all work together. And half of the time you still get the wrong web page on your screen. So, or there's an error that's actually displayed to you.
Which side does it actually do it on, like the sending side or the receiving side?
So the adding of the codes or the CRCs, that's happening on the sending side. The validation is on the receiving side, and the validation on the receiving side would be then at different levels. And oftentimes, if the packet needs to go back, you have to contact the sending side for that. Yeah. So they both cooperate on this. So now that we've discussed a little bit of how we recover the data and how we detect it, how come does it even happen, right? I mean, if zeros and ones are so simple, why does it happen? Well, it happens because between the server that's sending the data and the workstation that's receiving it, there is a wire, and that wire is subject to all kinds of environmental issues or interference from other devices. So we start with white noise, which basically is just the environment that's there. And white noise just is going to introduce a certain disruption of the signal. Impulse noise would be when, well, white noise is there always. Impulse noise is when something happens. You turn on the microwave and it draws energy and suddenly it creates electromagnetic field, and this creates a wave that influences the wire that is somewhere nearby. And you can see that at this point the noise filtration software is going to get confused, and it has to make very quick assumptions it has to figure out, is it a 0 or a 1? And it gets it wrong sometimes, which is why we then have to reach for a parity check or a Hamming code or CRC. Here's a great example of how impulse noise, so this burst of errors, how this is going to work at higher frequencies versus lower frequencies. So the fast speed right here, you can see that we can move a lot of data very, very quickly. High frequency transmission, a faster speed. But when impulse noise takes place, we're missing multiple bits here, multiple problems. So one of the solutions is to slow things down. Okay, let's drop your connection speed, and now the zeros and ones are more distinctive. You can tell them easier, and so if you have this impulse noise, we can, let's just say that right here, the filtration software would say that's a 1. And then that's a 0, and that's a 1, and we move okay without an error. Whereas at the high frequency here, we would definitely not be able to figure out what's what. So if you recall modems, oftentimes if you have some issues with connectivity, they'll drop you in speed, because the lower speeds are going to be more resilient to some of this noise. Here's another problem that takes place, and that is we have either wires close together, or maybe we have overlapping frequencies, and you can actually hear the transmission from the other device. So let's say you have a baby monitor, and someone else has a phone on the same frequency in another household. You could hear the conversation in your baby monitor. So the crosstalk takes place. Echo is another example. The wave is exaggerated, right? So it's not that big in a wire. But basically, the principle is that the wave, as it has its frequency, it is possible for the wave to bounce off the end of the wire and go right back in. And that's what produces the echo, which is why patch cords that we create for networking, you can't just cut the length that you want. Okay, there are certain lengths that these come in because of where the wave is going to end. So that's just another example of interference that would take place and possibly create issues. Okay, so here is an example of another problem in transmission, that's jitter. All of this, or the creation of the zeros and ones in the wave, is in the signal, is based on a clock. So imagine that this is 2 seconds, then this is 2 seconds, and this is 2 seconds, right? It has to be predetermined. Well, if the clock has some issue, so we have a timing issue here, we end up shortening either the zeros or ones, and that will produce a problem with the signal, a jitter. And of course, then we always deal with attenuation. If you use a wire that's too long for the specs, then attenuation is going to be a serious issue because the signal just can't go that far. Which is why in the error prevention, it says observe the stated capacities of the media, which includes both the possible speed on the media as well as the length of the wire. And those work just like healthcare does, right? If you can prevent some diseases, it's going to go much further than trying to solve those problems later on. Properly shielding cables, it makes good sense. At some point in the future, we'll talk about wireless networks in terms of a home LAN, and then how you can position the home radio so that you have best coverage. All right, and those are some of the solutions that not only, of course, deal with cabling, but with wireless. There's some preventative maintenance that you can do so that the packets come to you in a better condition. All right. And so that takes us through some of those ideas that we discussed first. And I did want to talk to you about parity and Hamming code in the first 10 or 20 minutes of your attention span. Otherwise, things get more fuzzy. But that's what we discussed. We talked about parity checks being a set of numbers that's verified by one more bit depending on the number of ones inside. The even number of ones does not require a confirmation, whereas an odd amount of ones, we would add a 1 to make it even. Excellent. So parity checks. Here is the example of a longitudinal or block parity. And so it allows us to actually fix a bit. Yes, please.
Okay, so the data is sent in a string.
Mm-hmm.
So how does it, like, put it in blocks?
Okay, yeah, so I put it in blocks for the need of us having a visual, confirmation. Okay, so right here, let me undo. I think I at some point, oh, there's only like 2 undo buffers here. So if there are spaces here, okay, which again this is all in a single stream.
Mm-hmm.
The computer does not have to put this together like we do in rows so as to calculate the ones and zeros. It can do that within a stream, but the stream is put together initially by a device. So we read in a picture, and then we have the opportunity to split that into smaller pieces, and as we take the first piece, we can add the parity to it. As we take the next piece, we add the parity to it. And then we have to remember what we sent, because we're going to send the confirmation of the bottom parity with it.
Okay.
And all it flows in one line, but for needs of our explanation, actually it's split into a block lookalike.
What was it? The row parity is added to the byte, right?
So the row parity is added to the row.
To the row.
Yeah. So if we were
And
to
then at the end you would send the column parity.
all right. So here we have another set, and it really at this point doesn't matter how many. In the standard, it'll be defined how many data pieces you have per each parity bit. So I'm going to mark parity here as just a letter P, all right? Because at this point it doesn't matter what we put here. So here's P, and this is our parity at the bottom. So the system does not have to put it into a matrix, right? It'll just send it to the left from here. So it sends this data out. All right. With the Hamming code, what we had here was the first 2 bits were parity, then the first bit of the data, then parity, then 3 bits of the data. And so and this actually is the Hamming code standard for this 7/4 arrangement.
And it just repeats that for the next one.
Right. So then it takes the next piece of data, applies the parities, move it along, and then on the other end, they'll read it out. But the sequence of it is all defined by the agreement or the protocol that they agree on. Mm-hmm. Great. So that's parity check. Checksum, right? Checksum is when we add together the values of, like in ASCII code, the value, and then we end up with a number. Checksum is this example right here. Okay, and then the cyclic redundancy checksum allows us for a very efficient dividing of large numbers. So the moment you can take large number, not just 4 bits at a time, but large number, the speed of the entire operation is improved. So even when we read from the hard disk, we feel like we have the time to do that. Okay, so how do we deal with this error detection now at a higher level, where we work with the packets, not just the zeros and ones? Well, we send acknowledgement. Okay, so we receive the data, we send acknowledgement, then another piece of data comes along, and if the data does not arrive in time, we can say a timeout took place. Resend the data. See, because at some point, it's not just the quality of the packets, but it's their sequence and the fact that they come in a timeout. We can't afford to wait forever. Maybe the device is turned off by now, right? So there are other errors than just the quality of the packet. There's also there's also the error of the timeout. It didn't come in time, or the error of sequence. It's out of sequence. Okay, the sliding window allows us to utilize the media a little bit more efficiently. Instead of acknowledging every packet, we can say send a whole bunch of them. We'll acknowledge and verify the whole set, then send the next piece. It's more of an optimistic way of doing it, and it works well, especially when you have a small pipe of connectivity, and that's why it's been developed years ago when the connectivity was at much lower speeds. All right, so let's get back here to an example. Let's see. All right, let's look at this example right here. So what we start with, and let me see if I can make this bigger. This one. So what we're starting with is bytes from 2001 to 2400, and those arrive. The next one has some kind of a problem. They're lost. Next we have 2601, which is out of order. Okay, we track that, and it's out of sequence. The zeros and ones are perfectly fine, but it's out of sequence. So what we can do is we can send a message back to the sender to say, could you resend 2401? And then it will do that. It'll resend the very packet that was lost before. So on both ends, the sender and the receiver, there is a certain amount of buffering that takes place, so that we have a pool of packets. In case they're requested, we can send them. And notice that the 2601, it came out of order, but we keep it in the buffer anyway, so that it doesn't have to be resent. See, it's sort of a different level of efficiency. But it allows us to verify, and this is the sliding window, so you can see there's a whole set of packets that are sent at the same time.
What was that last? That Act 2801, is that like a verification?
No, so that's a request for the next sequence of packets. So this was 2401, and so the missing one came in. But now we are in charge of verifying the sequence. So we know that we have now 2401 to 2600, we have 2601 to 2800. Give me the next one, 2801.
So it doesn't discard the one that came in.
Exactly. The idea for efficiency of it, it says I'll hold it in the buffer. You see, the browser that's downloading an image, it needs things in sequence. It's not going to do the buffering for the network device. It's the network device that's responsible to deliver it in the correct order. Yes?
Okay, so from an efficiency standpoint, it would be better to have a larger buffer, be able to take a bigger packet at one time, or take smaller packets and have a smaller buffer, but do it more repeatedly faster, I guess.
Yeah, I don't know. And this is where, over the years, along with the theory of it, some of those practical tweaks make companies great. Like Cisco, has some experience with this, and they've optimized. That's what optimization of these protocols will do, to figure out which exactly balance of packet size versus amount of acknowledging versus the buffer that you have. And this, when I talk about CRC, the polynomial that's used is also today optimized, because other ones are not working so well, are unable to verify as many possible problems. So now we can optimize them as time goes on. Yes.
But also, it doesn't realize that it didn't get all the information until it sends that next set of bytes, because I see it saying 2601 to 2800 before it.
Right, so in this example, it just sends things out, okay? And it's optimistic, the sliding window. So if one gets lost, it's up to us to say, whoa, hold on. Could you resend the missing packet? And then it'll start sending the data back in. But this only verifies the sequence, right? So we have other mechanisms that actually go inside of these packets and say, are all the zeros in check? All right. And if you want to learn the Hamming code the hard way, then you look at this graph right here. All right. But this is exactly the same what I was showing on the board with the circles. You see, this right here is a circle, and this is a circle. And if I was to do this differently, I can say, okay, this one right here, which is this one right here, it takes care of the two zeros, okay? And then this one right here, the zero takes care of the two ones. And then this zero takes care of, let's see, this zero takes care of actually never mind, they take care of three at a time. So one takes care of two zeros and a one. There we go. And this one does two ones and a zero. This one does two ones and a zero. And so then the last one, this zero takes care of two ones and a zero. Anyway, you get lost in that very quickly when you present it this way. Okay, but this is the same idea, Hamming code that allows you to verify multiple bits. And by the way, this is actually a different code. You can see that they are able to send B12. See, 1, 2, 3, 4, 5, 6, 7. So there's eight bytes of data with 4 bytes of the code itself. But definitely a more complicated way of explaining what happens there. Yeah, so 8-bit character and 4 bytes of checking code. All right, very good. So now what I'd like to do is, if you could open Blackboard and go to week 7, you'll find an exercise there in working with parity and working with some of the principles that we just discussed. All right, so let's see. Great. So if we look at the error correction lab, the first couple of questions deal just with parity. So you are to determine whether to add a 0 or a 1 on the end. And just pay attention to the fact that the first one is the even parity, the second one is the odd parity. Next, a little bit more complex set. This is our block parity, and you're going to verify the parity for the first row, add a number at the end, second row, add a number, third row, so you'll create one more column at the end, right? Then you'll verify the first column, second, and the new column as well. This will give you 8 bits at the bottom, and so you take those 8 bits and plug in as your answer. It might be helpful to do this with a pen and a pencil, or you can put it maybe into an Excel spreadsheet or something like that.
How do you generate?
How do you what? Is it, oh, it's a scientific word of some special kind.
Okay.
So you re-ate the parity bits right after lunch. Okay, so now So 8 bits right here as an answer. Does that make sense? Okay, next we have question 4. Hello is just a set of characters. You need to find somewhere on the internet the ASCII table and figure out what numbers need to replace these characters and then sum those numbers together. Just like what we did here with our example of GRCC. To locate the numbers and then provide the answer, and then the answer in decimal system allows us to answer this correctly. All right? Well, let's see how this might work for us. And if you have questions, raise your hand. I'll be happy to help you with that.